Okay, continue from where we were on last lecture. We started to talk about how to balance a redox reaction. Okay, the example we had is here, bromine reacting with uranium 4 plus ions producing bromide ions and UO2 plus ions. Okay, and the method that we're having is by steps. The first step is identifying half reactions. Okay, and this step should be very simple and straightforward, just simply looking at what turns into what. Okay, your bromine is turning into bromide, your uranium is turning into UO2 plus. Okay, so this reaction can be broken into two half reactions. Bromine Br2 molecules turns into bromide ion. Okay, let's not get that number in yet. Okay, and then uranium 4 plus ion turns into UO2 plus ion. So these are our two half reactions. Every redox reaction, because it's definitely having oxidation half reaction and reduction half reaction, so every redox reaction can always be broken down into two half reactions. All right, now step number 2 is balancing all elements except for hydrogen and oxygen. All right, so bromine obviously is in that category. Bromine molecule, Br2 molecule turns into bromide ion. Each one bromine atom is turning into a bromide ion. So there's 2 bromide ions here. And the other one contains uranium, but on both sides you have 1 uranium. So that one is self-balanced. You don't need to really do anything. Okay. Number 3. Use water to balance oxygen. Now, of course, after step number 2, you see that our bromine is balanced, our uranium is balanced. The only thing that's not balanced yet is the oxygen that contained in UO2 plus ion. Now, so first half reaction, there's nothing to do there. You don't have oxygen involved in here, so obviously you don't have to bother. Now, but the second one, I have 2 oxygen on the right side, no oxygen on the left side. And since we're using water to balance oxygen, then each oxygen atom need to be balanced by 1 water molecule. And we got 2 here, so plus 2 water here. Yeah. Now our oxygen is balanced. Step number 4, use H plus to balance hydrogen. Okay. Now, by adding water into the second equation, you're also introducing hydrogen into it. Yeah. And those hydrogen obviously need to be balanced. Now, notice that this time we're using not H2 molecule, not hydrogen atoms to balance the hydrogen in the equation. The reason of that, of course, is that both H2 molecule and hydrogen atom don't exist in a aqueous solution, in a solution environment. So nothing to be done again for the Br2 half reaction. Okay, still Br2 turning into 2 bromide ion, but this one, since you have 2 water on the left side, that means 4 extra hydrogen on the left side. And I'm going to add 4 H plus ions on the right side to offset the hydrogen. And of course, introducing H plus in your solution kind of tells us that this is in a acidic condition, acidic solution, because H plus exists in acids. Okay, and if you're wondering, well, what about basic situations? Well, we'll discuss how to balance this in a basic situation in a little bit. But right now, we're using H plus. All right, so at this point, after step 4, okay, both of your two half reaction equations are now balanced with all elements. Okay, now, are we done here? And is it time for us to put the half reaction back together into a full redox reaction? The answer is actually no. Okay, because yes, getting the elements balanced is very important in balancing chemical reactions. Okay, but another also very important thing that could be ignored now is that in any balanced chemical equation, the charge need to be balanced as well. Okay, this is very important because now, just like atoms, okay, electrons can't be created or eliminated during a chemical reaction. Mass need to be conserved there. Okay, so, and the other thing is, well, this is redox reaction, and we know that redox reaction is all about gaining or losing electron. Okay, so an electron, how does electron reflected? How is electron reflected in a redox, in any reaction? Well, by charge. Okay, so step number 5, we're going to try to take care of the charge. Balance charge in half reactions using electrons. All right, so Br2 turns into 2Br. Now, what's the difference? This is 0 charge on the left side. It's a neutral molecule. On the right side, you have 2 bromide ion, 2 -1 charge. Okay, now how do you go from 0 to 2 negative charge? Do you gain electron or do you lose electron? Remember, electrons have negative charge, so you have to gain electron to get the negative charge. Okay, so this is gaining electron. Bromine gaining 2 electron and producing 2 bromide ions. And if it's gaining, remember our oil rig acronym? Yeah. Gaining reduction involves gaining of electrons. So this is actually a reduction half reaction. At this point, with the electrons, we can say that with certainty. All right, so the other one is 2H2O, U4 plus, UO2 plus, and 4H plus. So what's the total charge on the two sides? That's neutral molecule 0. This is uranium 4 plus ion. That's plus 4 total charge. This is plus 1 charge on a polyatomic ion. You don't have to remember this is a polyatomic ion. Okay. This is not on one of those polyatomic ions. You have to memorize, know the charge and everything else for this semester. It's just something that you see in a chemical reaction. That's all. But this thing has plus 1 charge each hydrogen. Remember, you put in 2 4H plus ions. Each one of them have plus 1 charge. So this is a total of plus 5 charge. 1 plus 4. Okay. Now, where do I put electron and how many electrons do I need? Electrons are -1 charge, so if I put it on the right side, +4 minus 1, +5 minus 1 equal to +4. So now with one additional electron on the right side, I got the second half reaction balanced as well. Okay, and this, of course, is losing electron. So electron on the left side means your reactants are gaining the electron. Electron on the right side means your reactants are losing electron, and losing electron obviously is signaling oxidation half reaction. Yeah. And whenever you get to this step in your redox reaction, now, with no exceptions whatsoever, you should always find the two half reactions, one of them having electrons on the left side, the other one having the electrons on the left side. Okay, they have to be on the opposite side. If you go through a redox reaction trying to balance it, and by step 5 you found that, oh, both of them have electrons on the left side, do not continue. Something's wrong here. Okay, your reaction is not called red-red or ox-ox. Your reaction is called a redox. You have to have the read, and you have to have the ox. Okay, and read means gaining electron, that means electron on the left side. Ox means losing electron, that means electron on the right side. So it has to be on different sides for the two half reactions. If they're on the same side, there's no way you could continue in the next step. Okay, because the next step is combining half reactions. So, in a way, that the electrons cancel. Okay, no balanced redox reactions, full redox reactions, okay, would have electrons in them. Okay, now, and when you really think about it, this should absolutely make sense. Okay, now, because however many electrons your oxidation half reaction lose, okay, have to be however many electrons that your reduction reaction gain. You don't create electrons out of nowhere, and you don't make electrons disappear in thin air. So these two have to equal. But how do I make them equal, though? Because if you look at our example here, on the reduction reaction, you're gaining 2. On the oxidation half reaction, you're only losing 1. Now, can I make it lose 2? No, you can't. Because if you add a 2 for your electrons here, your charge is not going to be balanced. We didn't go through all this trouble, all these steps, okay, to have an unbalanced half reaction. Okay, so how should I think about this? Well, think about it like this. Okay, this half reaction needs 2 electrons. Each time this reaction happen, you're only making, or you're only releasing 1 electron. So how do you get the 2 electron that the reduction half reaction need? Well, you're going to have to make the oxidation reaction happen twice. Because happen once, you get 1 electron. Happen twice, you got your second electron. And those 2 electrons are what the bromine molecules need. So, all right, so 2 electron bromine, 2 bromide, and then 2 times the second half reaction, that would mean 4 water molecule plus 2 U4 plus ion producing 2 UO2 plus ion and 8 H plus and 2 electrons. So everything gets doubled. The whole reaction happened twice. Now you can combine them, add them up, left side to left side, right side to right side. And obviously, your 2 electrons are going to be canceled. Now you have both of them on the 2 sides. And what you got left from there after canceling the electron is bromine plus 4 water plus 2U4 plus produce 2 bromide, 2UO2 plus, and 8 H plus ion. And once you combine it, that will be your fully balanced redox reaction equation. Now, before you move on and say, I've completed the process of balancing this redox reaction, no. I want you to do an inventory check. By doing inventory check, I mean you want to make sure that everything that you have, okay, on both sides are equal. So left side, right side. Okay, let's start from the first element, bromine. How many bromine you have? You have a bromine molecule, that's 2 bromine atoms, and you have 2 bromide ions, so that's 2. Bromines balanced. The next one, let's say hydrogen, 4 water molecules. So on the left side you have 8 hydrogen. On the right side you'd have 8 H plus. So that's also 8. Oxygen, you have 4 water molecules, so 4 oxygen, and you have 2 UO2 plus ions. So 2 times 2, that's also 4 oxygen. And then uranium. You have 2 uranium 4 plus ion, that's 2 uranium atoms. And then you have 2 UO2 plus, so also 2. Now, the last one, no. These are all your elements. Everything checks out, but I still have one more thing. In the inventory check, the charge. You gotta make sure that on your left side and on your right side of your balanced redox reaction, the charge are equal. So on the left side, that's 0 charge, neutral molecule, 0 charge, neutral molecule, and 2 4 plus ion, that's total of plus 8. So total is plus 8. Now, on the right side, you have negative 2, positive 2, and then 8 plus 1 charges of hydrogen, H plus ion. So negative 2 plus positive 2 is 0, 0 plus positive 8 is plus 8. So everything checks out. You have a accurately balanced redox reaction here. And obviously this reaction happens in an aqueous situation with all these ions and also with H plus ions in the solution, which make the solution acidic. So this is under acidic condition. All right, so the next thing is, what if I just say, for the sake of our argument, well, this reaction happened in basic condition. What are you going to do? Go back to our, original process. Now, when we change this to basic condition, does this mean that I need to start from scratch and do this having a different sets of steps? Okay, the answer is actually no. Okay, you don't have to. Matter of fact, from step 1, 2, 3, and even 4, we want you to keep using the same procedure. So for basic condition, take a look. After step number 4, we have bromine turns into bromide ion, water plus U4 plus equal to UO2 plus and H plus. All right, so what we did earlier here. After step number 5, when we balance both half reactions, okay, you can very easily tell who's gaining electron. Whoever have the electron on the left side is gaining electron, and who's losing electron. Whoever have the electrons on the right side is losing electron. And that gave you reduction and oxidation. And if the reactant Br2 is going through reduction, what does that tell about his role? And that makes this guy, whoever goes through reduction, is your oxidizing agent, and U4 plus is going through oxidation. Whoever goes through oxidation is your reducing agent. Okay, so doing the half reaction can give you a very clear and very easy view of identifying the different roles your different reactant played during the process. And now, you know the method now, and this really need, okay, all right, let's BR2, U4 plus, UO2 plus, and BR negative. No. In basic condition, step 1, identify half reactions, exact same way. Step number 2, balance all other elements except for oxygen and hydrogen, same deal. Number 3, balance oxygen with water, same deal. Number 4, balance hydrogen with H plus, same deal. All right, so the first 3, okay, is easy to understand, okay. Those 3 steps, getting your half reactions, balancing everybody else, and even balancing oxygen with water, okay, you can imagine they're the same in regardless of acidic or basic condition, because none of those steps and none of those half reactions that we have, okay, really shows anything related to acidic or basic condition. This is where the argument is, okay. You're already in basic solution. How can you use H plus? Okay, well, we're using H plus to really just simplify the process. Okay, we're gonna get rid of it, okay, and in the way that basic solution would handle it. Okay, but this step here stays. All right, so after step number 4, what did we have? Let's go back. Let's have those 2 half reactions. Br2 turns into 2Br negative, and 2H2O plus U4 plus UO2 plus 4 H plus ion. So this is what we have after step number 4. Okay, so now this is where the basic condition starts to kick in. Okay, and we're not gonna change our step number 5, 6. Actually, the way we're gonna do it, we're gonna add another step. I'm gonna call it step 4A. Okay, so like step number 4 now get one amendment that we need to apply in basic condition. Okay, and that amendment is use hydroxide ion. Remember the basic condition to balance to neutralize, not to balance. Sorry. All H plus. Okay, now, all right, so the first half reaction has no H plus in it, so really the step 4A doesn't affect it one way or the other. Okay, now, but the second one does have H plus. All right, so what I mean is that now you have 4 H plus made in this reaction, in this half reaction. But we also know that now you're in basic condition. Okay? In any basic condition, in a basic condition, you know what's going to happen to H plus ions. Remember? H plus ions and hydroxide ions, they're soulmates. Okay? Once they see each other, they're going to get together. And you made some H plus in a basic condition. These H plus are going to be caught by hydroxide ions. Each one is going to be caught by one hydroxide ions, and you have 4 of them. So, of course, we're going to use 4 hydroxide ions to catch it. Now, but unlike the 2 previous steps, 3 and 4, where you just use something, okay, and as long as you balance the oxygen, the hydrogen, you're all good. Okay, here, you can't just limit yourself to add 4 hydroxide on the right side. Why? Well, look at this. Remember we said before our step number 4 in acidic condition, okay, in our step number 4 in acidic condition, is that after step number 4, all your elements are balanced regardless whether they are something else or hydrogen or oxygen. All the elements are balanced. Now, this is what I have in the box here is a half reaction that's already established element balance. Now if I throw 4 hydroxide on the right side, do you still have a balance? Of course not. Instead of 4 hydrogen, now you have 8 hydrogen. Instead of 2 oxygen, now you have 6 oxygen. Okay? Now, if that's the case, what do I do? Like, how do I not lose the balance? I already had the balance, I don't want to lose it. What do I do? Well, easy. Now, you added 4 hydroxide to neutralize all your hydrogen, okay? How do we maintain an equation to still be equal if you add something to one side? Well, add that same thing to the other side. Okay, so same amount of same ion hydroxide is going to be added onto both sides. The only difference is that on the left side, now there's no H plus. Okay, so nothing's going to happen to it. But on the right side, these two, they're soulmates, they're going to get together, they're going to give me 4 water molecules. No H plus, no more. Okay, again, basic condition. Now, and of course, when you made water and you already have 2 water there, so you can always cancel the 2 water and turn this into 2 water. Okay, so now your 2 new basic condition balanced half reaction are going to be Br2, 2Br negative, 4 hydroxide, U4 plus, UO2 plus, and 2 water. And once you add this step number 4A and completed it, okay, we're back on track. What's our step number 5 before? Step number 5 is balancing charge using balance charge with electron. Okay, so let's do that. Br2, 2Br negative, 2 electrons on the left side, charge is balanced. We already talked about that. Okay, now, the other half reaction, that's a hydroxide is -1, 4 of them is -4, and U4 plus by itself have +4, -4, and +4. The total is 0 charge on the left side. And then +1, 2 neutral molecules, so total charge would be +1. How do you turn turn +1 into 0? Well, if your +1 is meet with a -1, then you have the neutral charge of 0. Well, guess what? Electrons just happen to have a -1 charge. So 4 hydroxide plus U4 plus producing UO2 plus, 2 water, and 1 electron. Oh, sorry. Don't know why I did that. So on the left side, it's 4 negative, 4 positive, 0. On the right side, it's +1 and -1, 0. So now you have 2 completely balanced half reaction. Now, step number 6, same. Combine half reactions to cancel electron. Again, now, you should have, for both of the half reaction, even this time it's in basic condition, okay, you should still have the 2 half reactions, one having the electrons on the left side, the other one have the electron on the right side, and if they come to the same side again, then you made a mistake. Okay, some things probably got to be changed in your previous steps, but we do have them on the opposite side in this case. So let's see, how do I cancel them? Same deal. Each one set of this reaction only produce 1 electron, so I need it to happen twice so that I can have 2 electrons to give to bromine. Yeah. All right, and then add them together. Yeah. The electrons are going to be canceled, so I'm not going to bother with it. And Br2 plus 4 hydroxide doubled, so 8 hydroxide and 2 U4 plus ion. And on the right side, I have 2 Br negative, 2 UO2 plus, and 4 water molecules. Now that is your balanced redox reaction in basic condition. Now, and again, let's do our inventory. Left side, right side, okay, and starts with the first element, bromine, 2 bromide, 2, 2. Second element, oxygen, okay, 8 oxygen, 8 hydroxide, 8 oxygen here, 2 UO2 plus, so that's 2 times 2, 4 oxygen, and then 4 water molecules, each has 1, so 4 plus 4, so 8 and 8. Hydrogen, 8 hydroxide means 8 hydrogen, and then you got 4 water, so definitely 8 hydrogen. Yeah. And then uranium, I have 2 uranium here, 2 UO2 plus ion here, so 2 and 2. And then the last thing, the charge. On the left side, 0, negative 8, plus 8. Total of 0 charge here. On the right side, negative 2, plus 2, 0, so 0 charge there. So this is a good, balanced redox reaction. And you can see now we have balanced the same redox reaction in both acidic and basic conditions, and essentially using the same method, okay? And almost identical steps. The only difference is that for basic condition, you have an added step between step 4 and step 5. And that's where we have our step 4A, okay? Everything else is the same. And now, for those of you who's taken Chem 110 here in WVU, okay, a typical method that we use to balance redox reaction that you learned in Chem 110 class is the arrow method, okay? And I would think a lot of you would feel, and probably those of you who took high school chemistry or AP chemistry before have seen the same method, okay? Now, if you used arrow method before, and you feel like you're very good at it, and you never had mistakes doing it that way, you're more than welcome to stick to your arrow method in balancing redox equations. And matter of fact, arrow method don't break things down into half reactions, okay? And it's probably quicker in getting all the correct numbers for your equation, okay? If that one is quicker, okay, simpler, why do you give us this half reaction method? There are actually 2 reasons that in Chem 115 I stick to half reaction methods, okay? Number 1 is that by breaking down a redox reaction into half reactions, okay, you have a much better understanding of the oxidation, the individual oxidation and the individual reduction process, okay? You would be able to tell, okay, who's gaining electron, who's losing electron. And now, for example, in this case, okay, now, if you're doing arrow method, okay, although you're still drawing arrows and you're still trying to figure out who's gaining, who's losing how many electrons, you don't get to directly see what did the oxidation half reaction or what did the reduction half reaction use or made during the process, okay? The half reaction method gives you a very clear-cut, very direct view of each half of the reaction. And this is not just useful to have a clear view, okay? When it comes to a very important aspect of chemistry, electrochemistry, okay? That's where people study batteries, what's going on inside battery, or electrolysis and those type of chemical process. In electrochemistry study, half reaction is everything. Okay, everything is built from there. And I happen to be an electrochemistry major in my graduate school training. So to me, this is the foundational way of viewing redox reaction. So that's one reason. Okay, and the other reason is that the half reaction method gave you a very solid 6 steps that you can always rely on. Okay, remember, now you're going to be tested on balancing different complicated redox equations in your exam. And I'm still having that same opinion that I was telling you guys, that in an exam, you want the most foolproof way of handling a question. Something that you can do even when you're in duress, even when you are crunching for time, even when you're very, very nervous. Okay, you still got a very straightforward path, okay, to handle the problem. And half reaction method, with its fixed steps and very clear description each step what you want to do, okay, gave you that solid path to fall back on. Okay, it may not be the most direct and the shortest path, but it's a path that you can take, okay, when everything is kind of falling down on you. You can fall back onto a very basic 6-step method of balancing your equation. So whatever you do, okay, you can stick to the method that you feel more comfortable with when it comes to balance redox equation, but you need to at least know the half reactions, okay? And now, the other thing that half reaction how the half reaction method can help you, if you look at, okay, hold on. A ton of practice. It's not about knowing, remembering, memorizing the steps. This is more about, this is more about, can you, okay, balance a redox reaction equation, okay, as an exam problem quickly and correctly. And the quickly part needs you to be very familiar with the steps, with the process, and that comes with practice. So find examples and find practice problems in redox reactions and practice on it. You can find plenty of those in your textbook. All right, so the next thing we're going to get into, okay, is a special type of redox reaction, and they're actually not as complicated as some of these balancing redox equation problems you're going to see. Okay, and this part, it involves how the metals reacting with each other, and this particular type of chemical redox reactions we're going to introduce under the concept of metal, non-metal, activity series. Okay, now, and first, of course, let's go with the metal activity series. What is the metal activity series? Well, the metal activity series is introduced based on a particular type of redox reaction that we call single replacement reaction. Okay, what is a single replacement reaction? Now, this is one of the earliest discovered single replacement reaction. Scientists found, this is a long time ago, that if you put a solid piece of zinc into a solution, aqueous solution containing copper sulfate, okay, and let the zinc stay in there long enough, you would see that the zinc solid would actually kind of dissolve in that solution. Okay, you ended up making aqueous zinc sulfate, and you would also see metal copper start to accumulate on the surface of the zinc metal that you stick in. And also, the solution of copper sulfate is a very nice blue color, and zinc sulfate is colorless. So during that process, you would see zinc dissolving, and the color of the solution goes from blue lighter and lighter, and if you have enough zinc, eventually the entire solution is going to become completely colorless, transparent. Okay, now, and what happened here? The reason this type of reaction is called a single replacement reaction, okay, is that you have one metal going into a solution containing another metal, okay, replace that metal's row in the solution and kick that other metal out in the form of pure element. Okay, now, this is in comparison with our double displacement reaction that we talked about before redox. Okay, double displacement reaction are two ionic compounds exchanging partners. Okay, single replacement, okay, doesn't involve two ionic compounds or two electrolytes. One metal goes into another metal's solution, take its place, and kick the other metal out. Single replacement. Yeah. And so one metal goes into another metal's salt solution, replace it in solution, and also at the same time kick it out in metal form. Okay, and this reaction here, looks like a very simple and straightforward reaction. This reaction is the one that lead us to the first recorded battery in human history. The first battery that people ever made was based completely on this single replacement reaction. Yeah. And another thing, yeah, while zinc can do this to copper, okay, people also thought about, okay, what if I put metal copper into a solution containing like zinc salt? Is this single replacement, okay, a two-way street? What people ended up finding out is, no, it's not. You can put that copper into the zinc solution for as long as you want, okay, you will not see a thing. Okay, solution is not going to turn from colorless to blue color. You won't see zinc metal accumulate on your copper metal surface. None. Nothing would happen regardless of how much time you put that copper metal into a zinc solution. So single replacement reaction is a one-way reaction. Metal A can single replace metal B. That means metal B cannot single replace metal A. Okay, and in this sense, we say zinc is more chemically active than copper. Okay, zinc is more active than copper. Metal activity series. All right, we'll pick up from here on our next lecture.